at B finds the volume at B.
Okay, and then if it goes, I don't know, let's just say it goes whatever, but I don't want you know, isobarically straight out.
Like here?
C. You can't use the pressure and volume at C to find the pressure and volume at B with that formula because C is not adiabatic.
Correct. B to C is not adiabatic. It's another process, which in this case is isobaric. So isobaric would be volume at B over temperature at B would be the same as volume at C over temperature at C. And we could even put pressure at B and pressure at C, but since they're isobaric. But the point is, the relationship of pressure and volume are different in the different processes.
Okay, and we don't have an equation for work or for the adiabatics because it's just delta E, which is just LCV delta T, right? Because we don't really have.
Well, yes and no. I mean, you're right that delta E would be the same as the work because it's adiabatic, and you can just do NCV delta T. Yes.
Okay, we don't have. But you didn't give us. Did you give us a different formula?
I did not, but you have a homework one, and we can even look at it today. We get examples, but you could do this. You could say the work is negative the integral of pressure. And we could come back over here to the adiabatic process and say that is some constant and do that integral. That wouldn't be a hard integral to do either. So I have not done that yet in class, but only because if I can do this, I do. But that could be done, and that's not too hard. I mean, it's just a polynomial, so integrating a polynomial. It's not bad. All right, well, we're past time, and so let me go ahead and get us started here. Got lots to show you here today, and so I want to kind of go as quickly as I can, although not so quickly that it's not useful. And here's the idea is to show you a few more examples. You might remember on Thursday we did one long example that had, I think, almost every piece in there. So I thought it would be a good one to do before you went off for the weekend, and hopefully that helped you. But it would be helpful to see a few more. So in this first hour, let's do two more, maybe even a third example, then we'll call it quits and we'll go into chapter 22 because we're scheduled to start 22 and we're scheduled to have a test next Thursday, believe it or not. So our last chapter on thermodynamics, we're ready to start today. So first hour, let's do some examples. Second hour, let's get started in 22. That means on Thursday, we can finish talking about 22. That means on Tuesday, we can do examples from 22. And that means Thursday, we can take a test on 22. And so that kind of lays out the next 2 weeks. And we'll even go to the third week, and the third week will be spring break. And so there's the next 3 weeks for you. And by the time these 2 weeks are done, you'll be in need of a week of sleep probably. So just don't sleep for 2 weeks and you'll get all your homework done. Don, I didn't put it on the board here, but he did want me to tell you that he'll be doing a review then on Sunday. Sunday at 1 here in this room there. So pencil that in and write that on your calendars or whatever you want to do. 1 o'clock, 1 to 4. Okay. Before we get started, got a couple things. Here's this big box of homework that went around. Most of you have picked it up, but anything that was not picked up, I throw in here. You know it's in the lab by the printer. I thought I'd bring it to class and pass it around since the box is getting kind of full. Maybe with this many students this semester, I just need to get to a bigger box and realize, okay, people aren't going to pick it up, and I'll just put it in a bigger box by the printer. Second thing I wanted to mention was on Thursday, I passed out these nomination forms for Outstanding Lecturer of the Year, and I know that a few of you gave them back to me. Wanted just to comment that if you still have it, you're still thinking about it, great. They're due, I think it's the second week after spring break, or maybe it's the first week after spring break. But anyways, each day I see you, I want to remind you of that. And so hand it back to me or put it in one of the boxes around campus, whichever you feel the most comfortable with. the front of it, you might want to read the past winners, and the past winners, I'll say you can't nominate, but I guess you could nominate anything you wanted to do, but it won't really matter. They are not eligible to win a second time. Yes?
It says here there's no lab this week, is that right?
Oh, yes, and I should comment, there is no lab this week for the faculty lecture. This year's lecture is tomorrow afternoon, and I will be very much involved in that process, and so because I will be all tied up with that, there will be no lab. So that's why it says no labs. That's the reason behind that. So there's no change from the syllabus, just like somebody else asked about the test. There's no change. Those are scheduled on the syllabus. But you may not have noticed it since normally we do a lab every week. But there's an exception this week. No lab this week. Okay, well, with all that said, and I think I did see a second question. Did I? Okay. Let me try another example. As you know, we did number 23 before we left, and that had a lot of pieces to it. And like I said, if that made sense to you, then hopefully the rest of the chapter made sense. But let's try some more here. Let's try number 39. And so I thought it would be good to at least do 2 more in this first hour, and then maybe even a kind of a different one. But these ones with the PV diagrams, and the ones where we calculate all the energies or all the state functions, that is the pressure, the volumes, and the temperatures, are really the ones to see. And I'll say it again, but I think you're getting the point, but it really needs to be nailed down, and you'll see it again in the next chapter. Each of the processes that we have names for and ones we don't have names for, the heat and the work are path dependent, and so you have to pay close attention to what is going on and how the change was made in order for it to work. The good thing about the internal energy, it is a path independent. It is a state function, and those things make it a little bit easier. And I say that because 39, I think, really illustrates the 4 main processes that we've been talking about: isovola metric, isobaric, isothermic, and adiabatic. Listen to this one. It says the function E equals 3.5 nRT. I'll put that on the board here. E equals 3.5 nRT. Now, personally, I like to write that as 7/2 nRT. Now, basically, that means that CV is 7/2 R. Basically, that means we have something that has 7 degrees of freedom. They haven't really said what I have. I don't even think they're going to. They don't need to anymore because they have told me the equation for the energy. So the function E equals 7/2 nRT describes the internal energy of a certain gas. All right, so we know it has 7 degrees of freedom, but that's really all we know. A 2 mole sample of this gas is always going to start at a pressure of 100 kilopascals and a temperature of 300 Kelvin. All right, so starting with a PV diagram and emphasizing to you, draw these PV diagrams every time. They're like the free body diagrams. They help organize your thoughts here. So in this case, they say we have some kind of gas starting at 100 kilopascals for the initial pressure. They even said the temperature. What did I read? 300? 100 kilopascals and a temperature of 300. Good. And so I'll put a little 300 in parentheses kind of next to it. That's the temperature. Well, maybe I should even put a K for Kelvin so you know we're talking about temperature here. It doesn't look like they've given me volume. They did tell me that the number of moles is 2, so I've got 2 moles. Okay. For each of the following processes, determine the final pressure, the final volume, the final temperature, the change in internal energy, the energy added by heat, and the work done by the gas. So basically they're asking everything. Everything we can possibly calculate, they want to know, and that's why it makes a good example problem. I mean, we're going to cover everything. If you can follow this one, if you can do this one, you can probably do every problem in the in the book here. Okay, and so that is our little gas, if you will. Here's what it says. A, the gas is heated at constant pressure to a temperature of 400 K. All right, so A is pressure is held constant. We are going to be warming it from 300 to 400 K. That's their description on A. And so I'll do that in just a second, but watch the whole question here. B, the gas is heated at constant volume to 400 K. So here is the Isovola Metric process. We're still going to warm it from 300 to 400, but things are going to be different when you warm it at a constant volume versus a constant pressure. That was our whole discussion in our educational process last week. C, the gas is compressed at a constant temperature to 120 kilopascals. And so let's see if I gave myself enough room here. So C is the temperature is held constant. And then D, and maybe I should say the pressure starting at 100 kilopascals goes up to 120 kilopascals. And then D, the gas is compressed adiabatically. And so there are our four typical process, which I should point out, what does adiabatic mean? Q is equal to 0, right? We've done it so quickly that no energy can come in or go out. In fact, if I were drawing pictures on my PV diagram, what would this one look like? Constant pressure. Okay, straight horizontal line, right? So there is process A. What would B look like? Okay, straight line vertical, and again, the volume, but if the temperature goes up, that means the pressure would go up. And so that would be the process of B. So again, they say every time we start with this conditions, but one place we warmed it up and its volume got bigger and its pressure remained the same. The other one is its volume remained constant, its pressure went up as we warmed it. So two different processes. In fact, we got all four up here. The third one, C, constant temperature, what would it look like? Something like this. Right, that's that hyperbola. Right, that's the constant temperature. That's the process C, and we are compressing the gas. So we're going this way as opposed to expanding the gas. I would have drawn the curve out the other way here, but I'm compressing it, and I can tell that because they said the pressure increases. I think they even said the word compressed too, if I'm not mistaken. See, yeah, the gas is compressed at a constant temperature. And then D, the gas is also compressed, but it's adiabatic. What would that look like on here? Good, you guys are getting the idea that it will look probably something a little bit more like that in the process of D. And I think they said to the same pressure, if I'm not mistaken, I didn't put it up there, but it says the gas is compressed adiabatically to 120 kilopascals. So again, we're going to start at 100 and go to 120 kilopascals. So again, you can see kind of the makeup of this task, of this problem, and why I thought it would be a good example here is it will allow you to look at all the different combinations. And so they're asking for everything at this end. What is the temperature, the pressure, and the volume at the end? What is the change in energy of heat? Or what is the heat? What is the work? And what is the change of internal energy? Let's begin perhaps by just asking this question. What is the initial volume down here? And that's going to be true for all of these. So I might as well do it over here. But remember then, PV equals to nRT. So nRT over P is the volume. And they gave you enough information at the beginning to tell you what that initial volume would be. They gave me the 2 moles, so I'll put a 2 there. The R is 8.31, again, if I use pascals and cubic meters. And so I'm going to, since my pressure is given to me in pascals. The temperature here is 300 and the pressure is 100 kilopascals. That should give me my volume in cubic meters, which I could convert to liters, but I probably just should leave it in cubic meters. So 2 times 8.31 times 300 divided by 100,000 comes out to be, and it looks like it rounds to about 50 liters. That is 0.050 cubic meters. And remember, there's 1,000 liters in a cubic meter. So whether you want to call it 50 liters or you want to call it 0.05 cubic meters, which I will, 0.05 in units of cubic meters is probably the best way to handle that. So then as I go to fill in these different processes, I could say, all right, what is, say, the final pressure? What is, say, the final volume? What is, say, the final temperature? Well, the pressure one is the easy part, right? That is the isobaric process. So the final pressure is really the same as the starting pressure, 100 kilopascals. That's not so bad. Final temperature is not so bad because they even said this is what you're going to do. You are going to raise the temperature from 300 to 400. So those are the 2 easy ones. And then again, volume. To get volume, we can just use the ideal gas law here. And so this volume would be nRT over P. And in this case, my temperature has gone up. And so N is 2, R is 8.31, temperature is 400. Divide that by a pressure of 100, 1, 2, 3. And it goes up to 0.0. Looks like 6 cubic meters. And so that would be the first part of answering A, what's the new volume? Of course, and then I can do the rest of these processes, such as what is the change in internal energy? And I like to think about that one first. Maybe you can solve it, maybe you can't. But what's nice about that one is, remember, it's a state function. So you never have to worry about, at that point, whether or not it is an isobaric, Isovola Metric. And so I would encourage you to kind of start along those lines. It doesn't always work that way. Like any puzzle, you got to kind of do whatever works for you and whatever you see first and whatever begins to fit together. And that all depends on a combination of what is given and what do you notice first. But in this case, they gave me the equation straight up here, and that's just then the 3.5 nR and delta T. And so the delta T is 100. So 3.5 times the 2 moles times the R, 8.31, times a change in temperature of 100, and I should say a positive 100. And so 5,817 joules of energy, or internal energy, is gained by this particular process.
Normally we just use NCV delta T, right? But they gave us a different equation.
Yeah, well, they did not, they did, how can I say that? They gave us this equation, so I don't need CV. In fact, I used this equation to say what CV was. However, it could have been given the other way around, and it was in the first example I did, that they told you what kind of molecule it was. From that, you knew the degrees of freedom, which gave you the CV, which then gave you that equation. So it depends on what they give you. I would say this case was probably a little bit easier than the last one because they just gave me the equation. They didn't require me to find CV and then use it. Does that make sense?
Why did you use delta T if they just said T?
Well, they said the energy was T. So when I go energy final minus energy initial, I get blah, 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 temperature final minus temperature initial. Right? Okay. Okay, so there is part of it. But why don't I do the work? Again, this is isobaric. I don't know if it needs to be worked out again. We did it a couple of times, but maybe it's good to remember that it comes from an integral. But the isobaric is the easiest of the integrals. Well, maybe this one is actually easier. But with a constant pressure, this just becomes minus P delta V. And then so that would be the work. And so this case, the work is a pressure of 100,000 pascals, and the final volume is 0.066. The initial volume is 0.05, and that would be in pascals, and that would be cubic meters. So this is going to come out to be joules. So 3,000 times the quantity 0.066 minus 0.05, coming out to be 1,600 joules. And oh, I should put negative. Let me not forget that. Very, very important. This is negative. What does that mean? It's coming out of the system. Then that kind of hopefully makes sense because the gas is expanding. And so as the gas expands, the gas is doing work on the environment. Energy is coming out of the gas in the case of the work. But its change is positive. So obviously then the heat must be a pretty good number because you got to put in enough heat that not only increases the internal energy of the moving molecules, but as you are adding that energy, some of that energy is leaking out and doing work, if you will. And so going to the first law of thermodynamics, the heat would be this internal energy that it gained, 5,817 joules, minus a negative 1,600 joules. And that's why these two are added eventually here. When you put those together, 8 and a 6, what makes a 14? Carry 1 makes a 7. And so 7,417 joules is how much heat needed to be added to this. And so again, if it helps, this is what you're doing. You're adding a lot of heat energy. You're putting this under a fire, if you will. You've got to give it quite a bit of energy because as you give it over 7,000, over 5,000 remain, but some of it came out. That's why these two together actually equal that. Yeah.
Is it right also if we just say that's the Q is equal to NCP changing T, and then we say CP is equal to minus half?
Oh, certainly. You could go NCP delta T, yes.
And you can infer that CP is 9 halves.
And CP, right, is always one more R greater. So this would be 9/2 R times delta T. So
How do you use that equation for the isobaric?
Isobaric, that's what that means, CP. Right? And so yes, you can do that. And let's give it a try. This might be a good way to check to see if our answers, as I mentioned on the test, the good thing about these charts on our thermodynamics is you will know. There's more than one way to do it, and they should match. And you can check a lot of the times if your answers are self-consistent. And so if this doesn't match that, then I probably made a mistake along the way. And if it's a test, I'll keep kind of looking at it till I figure out what the heck I did wrong here. But let me give it a try. The number of moles is 2. 9/2 is the CP times R, 8.31, times a change in temperature of 100. And I get 7,417 And it looks like I got a 79, and I'll chalk that up to a little bit of rounding when the volume change was rounded here and rounded here.
Also, when we have so many degrees of freedom, you said other stuff happens too. So if you're all the way up there, then your numbers are going to be off if you're using NCP delta T. Right? Isn't that what you said?
I did, but that mistake occurs on a lower scale than this. So once they gave me this, then everything should work out fine from then on. So I'm not sure that's the cause in that case, but all right. But like I said, that one seemed like a good one, because let's compare and contrast that to all the different processes. How about this one, Isovola Metric? All right, so if I come over here and say, okay, what is the final pressure? What is the final volume? What is the final temperature? Well, I'll start with the easy ones. Obviously, the final volume is 0.05 cubic meters. That's what they said when they said don't change its volume. And so that little arrowhead going up is representing on our PV diagram this one. So our final volume is the same as our initial. And our final temperature was really given there because they said you're going to warm it up, again, from 300 to 400. They do want you to notice that as you warm it from 300 to 400 and you compare A to B, you will see that the work and the heat in step B is different than step A, because it depends on how the process went, even though you both went from 300 to 400. That's the point here. Let's see, the final pressure. The final pressure is going to be back to the ideal gas law here, but we can go nRT divided by the V for volume there. And so that final pressure did go up. It's 2 times 8.31 times a temperature now of 400, dividing that by a volume of 0.05, coming up with a pressure of, if I go ahead and round it up, to 133 kilopascals. So in my picture, it's gone up to about here, 133. And I got kind of lucky in my drawing, because I did draw it just a hair higher than these two. And I got lucky there. I didn't know how they were going to come out. But that one on C and D tell me they increased the pressure to 120. So this actually goes a little bit higher. This goes to 133 kilopascals. But I can begin to do the same thing. And I like to do the delta E first, especially since I already did it over here. And also, of course, I'll emphasize it's a state function. So all you need to know is the change in temperature. So isn't this still 5,817 joules of energy? Isn't it just going to be the same calculation, right? That one there. And so that's kind of nice there, that, hey, it's 100 degrees, the internal energy is still the same. But of course, what is different is this, particularly the easy one here. How much work is being done? Zero, right. That's the one where the gas hasn't done any expanding. So again, work is force times distance. So we have to have a distance involved. And in this case, we have no distance involved. Which means then the Q is just the 5,817, because those two added together have to give me this. Or, as you pointed out, we could go NCV delta T, which is the same as that, which will come out to be the same number. But again, notice I would use a CV here, as over here I would use a CP. But also notice then that the Q here is a much bigger number than the Q here. And so the work in the Q is different here than here, even though in both cases you warmed it up from 300 to 400. That's an important part of all of this. Also notice that the delta E is calculated the same here as the same here. And so again, that hopefully has gotten across to you. How about C? C again, kind of illustrating a different process here, is asking for all these same things, such as what is the final pressure, what is the final volume, what is the final temperature. Well, I'll start with temperature. What's the final temperature? 300. That's probably the one to start because it says it is an isothermal process. The temperature doesn't change. And so that one is going to be 300. However, they did not tell me volume, but they gave me enough information that C is I'm compressing it until I get to a final pressure. So that's going to be an easy one too, right here. What's the final pressure? 120 kilopascals. And then, of course, once I know that, I can go nRT divided by that pressure to find out then the answer to what's the new volume for this. So 2 times 8.31 times 300. I keep doing that same calculation. I should have just wrote it down. Divided by a pressure, now we're at 120, 3,000, and it looks like our volume has decreased to 0.0412 cubic meters. And so, as they said, you're going to compress it. So, sure enough, I have compressed it. Then we can talk about, well, what's the delta E? Yeah, good. I would, again, start with that one. It is 0. It's always related to the change in temperature, so it's the same formula that we've been using here and here. It'll always be that same formula. Of course, these actually change by 100 degrees, so we got a number. But this one is not changing its temperature. So delta T is 0, so the change in internal energy is 0. Now, don't get me wrong. That does not mean that the work and heat are 0. Let's talk about those. Maybe work is the one to talk about. How do you calculate the work? Yeah, okay, and it's probably worth going through this. Otherwise, you're going to feel like you need to memorize all these equations. But just remember, it's an integral. So if this integral is the easy one, it's 0. This one's pretty easy too. It's constant pressure. This one's a little more involved, but not too bad. If you do remember that both the pressure and the volume change, but you can convert pressure into nRT over V, and that this is a constant temperature, so it can be pulled out. Then, if you start at some initial volume to some final volume, you get minus nRT times the natural log of final volume over initial volume. And I think I heard somebody rattle that off, so obviously you had memorized that. Frankly, I can never seem to memorize all those. So I just kind of got to work it out each time. But notice, as the formula for work is different in each of the 3 cases, as it should be. They are, depending on the path you take, is the point. So in this case, when I go to put in some numbers, and I'll put them over here because I'm getting kind of low. You guys up front are going to have a hard time seeing this. But if I put in then the 2 and the 8.31 and the temperature of 300, and then the natural log of the final is 0.0412, the initial is 0.05. Notice, by the way, that that ratio is less than 1. The log of something less than 1 is negative. Negative times a negative make a positive, right? And so this is a positive amount of work, as it should be. Because remember, over here, the negative meant energy left it. So when a gas expands, it's doing work on the environment. Energy is leaving it. So every time a gas expands, we should have a negative number for our work. This is the opposite of that. This is here where we are compressing it. And so we are compressing it. We could say the environment is squeezing it. The environment is doing work on the gas. It is squeezing it together. Work is being done on the gas. This should come out to be a positive number. And sure enough, a negative and a negative make a positive. And so if I take a negative 2 times an 8.31 times a 300 times the natural log of 0.0412 divided by 0.05, I should get a positive number, and I get 965 joules. And so this is being compressed.
So I did it myself with the calculator, and I used a different rounding, and our numbers are off by like 50s. That should be okay.
I got 909.
Oh, 909?
I got 920. I mean, it's just a matter of rounding.
If it's just a matter of rounding, yeah, don't sweat it. Did it
0.04 without the 2.
here? What about here?
0.05.
Okay, because that's rounding, but you rounded the same as me.
The bottom one, I didn't do that one myself. I trusted
Ah,
you.
yeah. Oh. Actually, okay, I'm gonna try that one. Let's see if I can go back on this calculator. And so you just dropped the 2,
And it jumps up.
and you got 989. So 20 more.
Is this compressed?
So, yeah, okay. Anyway, so it's rounding. Yeah. No sweating. Yeah. And I will, hopefully, definitely see that when you're doing the exam. Yeah, and usually on this, when I'm grading this exam, I've noticed. I say, oh, this one's quite a bit off, and it makes me go back and look and, try students' numbers, and I go, God, their logic is all sound, huh? And then it's just rounding. So, but as you know, I seldom even look at this until I've gone through all that and just say, okay, well, their logic is right. Because if I saw that right there, I would totally understand what you did. It's just like, oh, okay, yeah.
We can use pressure as the ratio there too, right?
Yeah.
That's how you solve it.
Yeah, exactly. Yeah, I guess you could. Sorry, I had to think about that for a moment. But in that case, because it's isothermic, yes, the ratios of the volumes is the same as the ratio of the pressure, although they're the reciprocals of each other, right? And so final over initial is the same as initial over final. But other than that, sure. And the log of a reciprocal is just a negative, so if you're not really even paying too much attention to the sign, that's fine. And finally then, what about Q? Yeah, it's negative of the W, so I would just put a negative 965 or 989 and just call that good. And that's the first law of thermodynamics. And so, again, that's the nice thing about finding the first two energies, because the third one just adds up, and that's the easy way to get how much heat you're going to be. And again, notice then that the number is a negative number, meaning heat has to come out. Kind of makes sense. You're squeezing the gas. And as you watched me do in class many times, and we'll see it again here today as we get started with the last chapter, we'll squeeze this gas. And if you just squeeze it without letting heat come out, adiabatically, it warms up. In fact, we are back on that adiabatic trend. I kept thinking about you guys all day Saturday, thinking, I hope somebody is out there thinking about the weather, going, guy, where it's 81 degrees and in Santa Barbara, but it was actually cold in the desert because the air was coming down, it was shrinking, it was compressing, it was getting really warm, and it was all this adiabatic compression. And then we had a little cold front, and now we're back to the same thing. And so Southern California's weather is highly dominated by these Santa Anas constantly, these mild Santa Anas. We go from an onshore breeze to an offshore breeze. And that offshore breeze, we get that nice compression warming. And so we're going to have nice weather as long as we've got that compression warming here. Anyways, but this one, the heat would have to flow out, otherwise we would have warming. And so when the environment, in this case our air, comes down and shrinks, it gets compressed and stays, and warms up. But the only way to keep something at a constant temperature then is that the heat's got to come out. And that's what this is saying. So as it's being compressed, we got to make sure heat has a chance to come out. And I think, again, that's kind of hard to understand sometimes because its temperature's not changing. But you've still got to take energy out. If you didn't take energy out, its temperature would go up. Well, and then finally, the last case here, which I think is the harder of the ones here, is the adiabatic process. And again, what is the final pressure, what is the final volume, and what is the final temperature? This one I'll probably need some more calculation room. Fortunately, they did give me this one that says the final pressure is 120 kilopascals. But they have not given me those. And so this is going to take us back to the mathematical connection, and maybe I'll clear this part off the board of what is the connection between pressure and volume in the adiabatic process. And that is pressure times volume to a factor of gamma is supposed to equal a constant. So keeping that in mind, that would tell me my initial pressure times my initial volume raised to a factor of gamma would be equal to my final pressure and my final volume raised to a factor of gamma. And I do know these two. I also know that one, so I should be able to find final volume here. I am going to have to give a little thought about gamma. Gamma is Cp over Cv. And that's kind of why I brought this discussion up a little bit earlier. I need to find both of those, and this information does subtly bury inside of it what is Cv. And so Cv is 7/2 R, which means Cp is 9/2 R. And so we have a 9 over 7, which goes 1 2/7, 2857, 1 4, repeating forever.
14286. Well, yeah, the whole thing starts repeating.
Right. Well, it's a prime number. It's a prime number of 7. It's got to be 6 repeating forever. We'll stay away from number theory, but that's left for your math class. But anyways, that's it was a good question. I'm glad you brought that up. All right, but getting away from math and sticking to physics here is then this would be my factor of gamma. And so using it up here, pressure initial is my 100. So this is my 100,000. The volume is 0.05. I would be raising it to 1 point, how about if I just round it to a 2.9 here? And then that would equal to my, which one do I know? I know final pressure, 120,000 pascals, and then final volume raised to a power of 1.29. And maybe just for math reasons, I'll take an intermediate step and just solve for what is the volume raised to a power of 1.29, so that I can go 123,000 times 0.05 raised to 1.29 equals. Divide that by 120, 123,000, and come up with, so far, 0.017, and I'll just round to a 5 there. And I find these best to solve. This is kind of why I wanted to pause and say, why don't we raise both sides to a power that is the reciprocal of gamma? Because then you get just that, right? You get volume. And so taking that number and doing the little caret and then putting the 1.29 and hitting the reciprocal key and then hit enters gives me 0.0434 cubic meters. And so again, not a surprise that it has been compressed. But also, and hopefully not a surprise, it is not the same as the volume when we got the isothermal. And hopefully again, not a surprise that the isothermal is a smaller volume than the adiabatic. That's what we were trying to show here by saying it's a little steeper. Now my picture shows an extreme difference between these two volumes, whereas it looks like numerically there's not that much difference in their volumes, but this volume is compressed clearly and clearly bigger than the volume we got when we compressed it isothermically, as I would expect, right? And so there is my final volume. And once I have that, I should be able to get the temperature, because pressure times volume divided by nR should give me that temperature. And so that should be my temperature. So I'll take the 120, 123 kilopascals times the last answer I get, so I'll have less rounding there. Taking that number and divide it by 2 moles, is that what we had?
Yeah.
Okay, 2 moles. And then divide that by 8.31, and we are at 313 Kelvin. Again, warmer, as to be expected, than the isothermal process. So this squeezing did warm up its temperature, as we had seen many times, and you saw that little flash paper burn here. And so there's my processes there. Knowing that, then I can answer these other questions, such as, what is the change in internal energy?
It's the same.
Same as?
The work does it. What they gave us, no? The 3.5.
Okay, so it's the 3.5 nR delta T, right? So it's the same equation. My delta T, though, is only 13, right? And so that's, here the change in temperature was 0. Here the change in temperature was, well, I've erased them, but they were 100. So we haven't done one where the change in temperature was 13. That's why I wondered what you meant by the same. But the formula is the same here. So 3.5 times 2 times 8.31 times a change of only 13 degrees means that the change in internal energy is only 756 joules of energy, which helps me find the other two, because what's Q? 0. That's where we got started. That's the adiabatic process. So what's W? Must be the 756. So this gas that is being compressed adiabatically, of course, is a positive number. We are doing work on the gas. That's how much we did. And all of that work showed up as internal energy. That's why the heat went up, even though we didn't, that's why the temperature went up, even though we didn't add any heat energy to it. Yeah.
Which one is more accurate for finding the temperature? I used the PIVI over TI equals P final, V final over T final.
PIVI.
4 kelvins off, and then that changed my work. And that made my work off.
Oh, now, yeah, this could have a significant rounding, because this is only 13. So which one are you, this is one of those ones that you can get a huge number depending on how you round. But what did you say you used? PV?
Over TI.
TI, yeah.
Equals to P final, V final over T final.
Final, T, final. Well, that's what this is. So I'm not sure we did anything different.
I ended up 4 kelvins off, and then that changed my work a lot.
So if I go final pressure, 120, 123 kilopascals times a final volume. Oh, wait, what did you use for final volume?
That's right. I searched it.
Okay.
0.043
Okay.
over 0.05. Should have been 0.05 over 0.043.
Okay. Good. That's it. Good. Sounded like that was a little more than rounding. And then did we finish everything? Oh, good. So we have all those. And so, like I said, this was, I felt, was a good problem, because it had a lot of the processes, all 4 of them actually, and gave us a chance to look at those. And then hopefully, like I said, if all that made sense, I think you're in good position to do every problem in here, although some problems don't necessarily follow these four, I'll call it the four famous ones here, and the ones we give a name to. Which is why I thought doing this last one here would be helpful before we get started with the next chapter. How we doing on time? Looks like just about right there, maybe a little slow here, but let's look at 53. 53 is kind of this same process here, where we're going to draw a PV diagram and we're going to look at the process. It's just this one doesn't have one of the fancy four in here, but hopefully the logic is the same. It says this: a gas, well, it just says model air as a diatomic ideal gas with a molar mass of 28.9. Now they're probably going into that because air in this room is made up of many things. But most of them are diatomic, and most of them are nitrogen. So the molar mass of nitrogen would be 28, but we do have some oxygen, and of course we have some carbon dioxide and water. Both those are not diatomic, and they're, well, water's light and carbon dioxide's heavier. But anyways, so it looks like we got an average of about 28.9. So it makes sense that it's roughly diatomic, and it's roughly 28. That would be happening with the air in front of you. So that's why it says here, model the air as a diatomic ideal gas with a molar mass of 28.9 grams per mole. A cylinder with a piston contains 1.2 kilograms. I was going to convert it to grams, but we'll wait for that. 1.2 kilograms of air at 25 degrees Celsius and 200 kilopascals. Energy is transferred by heat into the system as it is permitted to expand, with the pressure raising to 400 kilopascals. So we went from 200 to 400. Throughout the expansion, the relationship between pressure and volume is given by this equation. There's the key. Pressure is equal to some constant times volume to the 1/2 power. A, find the initial volume. B, find the final volume. C, find the final temperature. D, find the work done by the air. And E, find the energy transferred by heat. And so if I begin, like every process, and look at a PV diagram, I will start something like this and say this is my original pressure. They say 200 kilopascals. They say it starts at 25 degrees Celsius. So adding that to 273 makes 298 Kelvin. Don't believe they gave me the initial temperature. Initial volume. But I think I can find it. In fact, that's one of the questions that I just read. But the real key is they say they are going to be warming it up, and what's going to happen is the pressure will increase until we get to 400 kilopascals. And when we get to 400, we stop. But they were nice enough to tell me the relationship looks like a square root function. And so again, it's not one of the fancy ones we have a name for. So I don't know what necessarily to call it. It's just a square root relationship. But that's what it would look like on a PV diagram. So it's not isobaric or isovola metric or isothermic or adiabatic. It's none of those fancy four that we talked about, but it is one that we can work with here. I'll start with asking, well, how many moles do I have? Yeah.
Can you describe a physical process in which that might occur?
Well, I guess I could come over here and kind of illustrate it by saying, okay, here's my gas in my container. It's leaking today. That's not good. Did I not clamp it hard enough? Okay, yeah, clamp's just being a little stubborn. Okay, so there is my gas. Yeah, let's see. So I guess I'm going to think about this. Could I emulate that process? Well, it looks like what happens is volume is increasing and pressure is increasing. So that probably means I need to heat it up quite a bit. And so for that to work, I guess I would have to be doing something. Here's some weights, so that's going to be able to add pressure on it. And so I guess I'm going to want to add a little bit of heat, but pressure, not so much pressure that the volume ever goes down, but keep adding pressure. There we go. Something to that effect, where the volume does get bigger and the pressure is getting bigger, and the only way to accomplish that is by adding quite a bit of heat to it. Yeah. And I would have to do it in the right rate in order for it to follow this particular pattern. All right, so here's the particular pattern. I'll start with number of moles. The number of moles then would be the 1,200 grams that we start with, and divide it by the 28.9 grams per mole. And so there's kind of the first part, a quotient. You were saying, how many of these do you have? You know, for every 28.9 grams, you get 1 mole. So I would divide the two. And so it looks like I've got quite a bit gas here. 1,200 divided by 28.9 comes out to be 41.5 moles. So 41.5 moles. That's a lot of atoms, as we already mentioned. 1 mole is a lot of atoms, 10 to the 23rd. That is, never forget how big that number is. Like I said, there's more molecules in a glass of water than there are glasses of water in all the oceans of the world. Or put another way, there's more molecules in 1 mole than there are sands and grains of sands in the entire world. Another one, I don't know if this has the same effect though, but there's more atoms here in 1 glass of water than there are stars in the entire known universe, which is quite a few stars too. So I don't know which is the more impressive way of saying it, but most scientists think there's about 3 times 10 to the 22 stars in our known universe, which
The observable universe? Or the universe?
Observable. Yeah, because something like 350 billion galaxies, 10 billion stars per galaxy comes out to be, don't quote me on those numbers, but some ridiculous amount of numbers there. But amazingly enough, there's still more atoms in a glass of water than all those stars. So there's a lot of them. Anyways, and there's a lot here. So there is how many moles I have. All right. Keep going with this, and then I can begin, I think, to answer these questions. The first question, what was it? It says, where did A go here? A, find the initial volume. All right, well, volume is nRT divided by P. That's always true, and so it would be true in this case, whether this be one of the fancy 4 processes or this be some other complicated one here. This is my connection. So this would be 41.5, this would be 8.31, this would be 298 Kelvin, and this would be 200 kilopascals. And so that should be my volume in cubic meters. So 4.15 times 8.31 times 298 divided by 1, 2, 1, 2, 3 comes out to be about a half a cubic meter. A little more than a half a cubic meter. Again, I guess that makes sense. We had so many. This desk in front of me is about a cubic meter. It's a cubic meter high, a little more than a meter wide, and about a little more than a meter depth. But half of this box, then, if we cut it in half, that's what they would be saying here. We've got that many moles inside of here. Now the pressure is twice the atmospheric pressure. So that many moles would probably be in a cubic meter at regular room temperature and pressure. So that's what we have to work with. So there's A. What is the initial volume? B goes on to say, find the final volume. Well, maybe that's best written as P over volume to the 1/2 equals this constant. That way I can write P initial over volume initial to 1/2 would be P final over final volume to the 1/2 power. That's the mathematical connection. And I think that's why this made a good problem, because it was not one of the standard ones. We're so used to saying, certain relationships because we always keep doing the fancy for. But there are other relationships, and this is what they've given to me.
Is this an ideal gas?
Yeah, it's an ideal gas. That's why I use this.
So would the P initial times P initial equals P final times P final work in this case?
I don't know. I don't think so. You said this, right? You said P initial over times equal what?
P final
Yeah?
times P final.
When does that work?
When we have T.
When temperature is constant. So that would not work in this case because we don't have constant temperature.
Given the C in the...
No, we are not. Bummer. It's one of the questions, though. Find C. But at this point, we don't know C. And notice I completely avoided it. It's really the same thing you did here, right? I mean, the way you got here is you wrote PV equals to nRT. So you said initial pressure, initial volume equals nRT initial. If it was a constant temperature process, you would say the temperatures are the same, and then you would say final pressure, final volume. You would put those together, and you would get this relationship, and you would completely avoid how many moles do you have, what's the final or initial temperature, what's R. You can completely avoid those constants by setting the two equal to each other. So this relationship works. It only works for constant temperature, and it avoids messing with certain numbers we may or may not know as long as they're constant. And that's kind of what I'm doing now. I am saying, look, this is some constant. I don't know it, at least not yet. I could probably find it. In fact, I know I could find it because don't I know pressure and volume initially? So I could get the C, and I think that's the next question. But I'm avoiding it, and I don't know if that's better to avoid it or not, but I certainly could and would come up with this relationship. In fact, I was going to square both sides so that I can then get that relationship, which would say what is the final volume. And so my final volume here must be the final pressure squared over initial pressure squared times the initial volume. And because in this case, I know that the pressure doubled. It went from 200 to 400. So this would be 2 squared times initial volume. So 4 times initial volume. And what does that become? That's a 20, that's a 4, and that's a 16. Is that the... How's that? Am I back? Okay, good. Get snagged down there. All right. But that's the final volume, if I did my math right here. You got the same number? Okay, good. And so there's B. What is the final volume? Well, let's move on then to C and say, okay, C, find the final temperature. Well, they haven't asked for C yet. Find the work done. Oh. I guess I'm going to need C. I think I'm going to need C eventually, but so far I'm not going to worry about that. But question C says, find the final temperature. And again, final temperature would be final pressure times final volume divided by N over final NR. NR. And so knowing then the final volume is here and the final pressure, I should be able to calculate also the final temperature. And so it's final pressure 400 kilopascals, good, times a volume of 2.056 divided by the number of moles, 41.5, divided by R, 8.31, comes out to be 2,384 Kelvin, a very high temperature. But again, going back to the whole process itself, maybe it's not a surprise because I've really got to warm this up quite a bit. I mean, not only is the volume getting bigger, but then the pressure is increasing on it, and the only way that's going to hold out is if those molecules are really going really, really fast, and that means the temperature has to be really, really high. Okay. But I think proportionally, though, that's not going to change the temperature. I mean, if we did this with a small volume, it's still, if it follows this relationship, it's going to have to warm up. But I agreed, it's a big volume. But I don't think that changes that answer. D then says, find the work done. Okay. Well, work, well, maybe I should put, so D, work.
Before you erase that right side right here,
Right here, yeah.
if you're just off by like, let's say your temperature is like just off by 1.
Are you back on this one?
Yeah. Changes your work a lot. If you're just off by 1 Kelvin.
Yeah, it would be 1 part in 13, right? Because it's only a change of 13.
Yeah, but then wouldn't that make your work wrong if you're doing it on a test or something?
No. I mean, make sure you write out every step. So like on the test, I can look at your logic. And then I can just say, okay, this is just where they rounded it. But when you only have a small temperature change of, that was a little more than 10 degrees. It was 13 degrees. But if you change by, 1 in 13, you're talking about 7% difference. Which isn't that much, but it's certainly noticeable. Yeah. So what was D on this guy? D, work. And again, probably the best way to handle that one is to go back to our integral. We certainly couldn't use any of the equations that we've memorized for adiabatic or isothermic or all those other ones because it's not one of those fancy 4. It's one we just got to go back and do the integral here. And so as I do the integral, I can replace it with CV to the 1/2 power. And so that's kind of this nice mathematical relationship. And so I think on this one to get a number, now I'm going to have to find out what is the value of C here, or at least do the equivalent of finding the value of C. Because again, this would be a minus a C, but when I do this integral, what do you get? Volume to the 3/2 power divided by 3/2 evaluated from some initial to some final volume. So I guess I'll write that as a negative 2c over 3 when I bring the 2 and the 3 over there. And then this would be final volume raised to the 3/2 power minus initial volume raised to the 3/2 power. And so now I need to actually then find the value of C before I can go further. But I think it's nice to always stop here and ask, does this come out to be a positive number or a negative number? And maybe I should ask, what should it be? Yeah, well, the gas got bigger, meaning it's doing work on the environment, so it should be a negative number. And I already have a negative in front here, and my volume final is bigger than my initial, so that's going to come out to be a positive. My final was where here, and my initial is here. So this is going to be becoming a negative number. And then the C can be calculated either from the initial conditions or the final, but I might as well start with the initial here. My value of C would be the initial pressure, which was the 200,000 kilopascals, divided by the initial volume, which was 0.514 to the 1/2 power. And so that's how I would get the C. And like we talked about earlier, I guess I could have got that back here and actually got the value of C, but I didn't need it really quite yet. Now I definitely need it. And so the final volume is the 2.056 raised to a power of, and I'll just put 1.5, make it a little easier to put in my calculator. And the initial is the 0.514 raised to a power of 1.5. And so there should be my work. And so got a lot of buttons to push on the calculator, but I think you're getting the idea. So 2 divided by 3 times 200,000. Divide that by 0.514 raised to a power of 0.5. I'll just hit enter along the way. Times then all that stuff. 2.056 raised to a power of 1.5. Oh, this is the new. Okay, guys, you need to tell me again. What do I do? Arrow down? How do I get out of the exponent?
To the right.
To the right. That's what you said. Yeah, thank you. All right. Okay, minus 0.514 raised to a power of 1.5 to the right. Close parentheses. Enter. Okay. So, a lot of numbers here. 4, 7, 9, let me round it up. 480 kilojoules. So that's thousands. So 480 kilojoules is the work done by this. What they ask next? Just find the final temperature, find the work done, and then finally E, find the energy transferred by heat. Pardon me?
Shouldn't that be negative?
Oh, negative, thank you. Yes, I dropped it off my calculator, but I was going to add it later. And yeah. And then E then is what is the heat? And again, I would kind of avoid the direct calculation of heat here and say that the heat is then delta E minus the work. And we've already done the work. And so really it comes back to our delta E, which is NCV delta T, right? And again, one last time before we move on to the next chapter, let me emphasize, this is not a constant volume process. Yet, I am using CV here because I'm calculating a state function. All right. So our number of moles was the 41.5 moles. CV would depend on what kind of gas you have. And I think that's, again, why the very beginning part of this says, model the air as an diatomic gas. So what is the CV? How many degrees of freedom do I have? 5. So this is 5/2 R. And the change in temperature, I think we did that somewhere. Yeah, there's the final temperature, 2384. 2384 and 298. Is that what this one started at? 298. And so 2384 minus 298 is 2086 times 5/2 times 8.31 times 41.5 moles. And so this is 1,798 kilojoules, 1, 2, 3, for the change in internal energy. And a positive number, as to be expected. We are really warming this up a lot. So the Q becomes the 1,798 good, minus a minus 480, just to make sure it's clear that I'm subtracting, and I'm subtracting a negative number, but add 480, and whoops, I messed up there. So 8, 9 and 8 make 17, carry 1, 12, carry 1 is 2. So there is the...
Is Q always bigger than E change in E?
No, Q doesn't necessarily have to be bigger than it. It depends on this sign. Right? If the work is a negative number, the answer is yes. So during an expansion, yes. But during a compression, no. And so it depends on the sign of that one. All right, well, that took a little more than an hour, but I think was well worth all the time, because those are the ones that students struggle with. And to understand 22, you really need to understand all this. It'll actually make 22 real easy once you understand that. So that's good and bad. It's another way of saying we're going to keep doing the same thing here as we start chapter 22.
Yeah. Did it say the problem is a diatomic gas?
Yes. Good point. Because I'll read it here. It says, model air as a diatomic gas with a molar mass of 28.9. So I knew that's where the diatomic came from, and I also knew that's where the molar mass came from. So when they said I had 1,200 grams, I could figure out how many moles. Yeah. All right, well, like I said, let's move then into chapter 22. And I'm hoping you will find this the most interesting of all the chapters, because now we are at the point where we can begin to do some real life practical applications. We have learned enough thermodynamics that we can really get into some complex problems. That's both the good and the bad about this whole class, is we go from different units, and about the time we really get to some advanced stuff, we leave it. And that's what's going to happen here. So if you're enjoying the thermodynamics, you will probably be sad that we're leaving it. If you're not enjoying it, well, you'll probably be glad we're leaving it here. But I hope all of you will at least see the final step here as how we can build heat engines and how we can use this in a practical sense. And that's actually the title, and that's where I want to begin here, is to show you heat engines. It's heat engines, and the second law of thermodynamics is what this chapter is all about. So chapter 22, the title says it is about heat engines. And that's about as far as we'll probably get today. It also says this is a great time to introduce you to entropy, which is really the second law of thermodynamics. Thermodynamics. And so we spent the last 2 chapters really discussing the first law of thermodynamics. And in fact, that's kind of where I want to begin. It may seem like kind of an odd start here, but I want to take you back to mechanics here. Oh, here's a baseball. Now that now that we are getting ready for our baseball season, but we got to get through March Madness first. But as we look at this baseball,
11 days.
could it hit the ceiling?
Yeah.
Will that hit the ceiling? Will that hit the ceiling? So it may or may not hit the ceiling. Well, what's the requirement for it to hit the ceiling? Oh, it has to have enough energy is what you're saying, right? Okay, so there's kind of these laws of nature, right? There's these restrictions of why things can and cannot happen. And one of the obvious one was conservation of energy. If this ball does not have enough kinetic energy, it's not going to hit the ceiling. It will hit the ceiling if it has enough energy. Fair enough? So doesn't the law of conservation of energy kind of dictate what can and cannot happen? All right. I'll try the same thing. Again, let's go back to our mechanics. Maybe I'll clear some of these things out of the way that we're probably not going to get to today here, but let's look at this card here. If this is level or nearly level, if I bring in a second cart and I collide it, and I'll do it so they stick together. This one moves, hits, and collides with it. And unfortunately, it looks like my track is not really level. See if I can get it more level. All right, so it collides, sticks. Still not level. Try it again. All right. And so, hopefully without taking too much time, let me just again bring you back to mechanics and say, could these two objects collide and just come to a complete stop? In other words, can all the kinetic energy get converted into heat? What if I put more weight on here? Will that make all the kinetic energy turn to heat? Still moves. Can I convert all that kinetic energy to heat? Without friction. Without friction.
Yeah, put enough weight on it. Yeah, exactly.
Is it always going to move a little bit?
There's no friction.
It is. If there's no friction, it's going to move a little bit. Why?
Because there's no friction.
Momentum. Conservation of momentum, right? So again, the laws of mechanics are conservation of energy, and in this case, our second one, our conservation of energy, put certain conditions on what can and cannot happen, right? And so when we begin to ask what could happen and what can't happen, these are what the laws of physics is about, right? These are what mechanics is all about. Well, I would say the same thing here. What is the first and the second law of thermodynamics really telling us about nature? They are telling us which processes can or cannot occur. So if you were to say, let's start here, and somebody were to ask you, for $1 million, can you take a moving cart, collide it into a stationary cart, any mass you want, and all of the kinetic energy gets converted to heat on a frictionless surface? The answer? No. The first part of it, conservation of energy, you say, well, that would work, right? Conservation of energy would tell me if I have all of this kinetic energy and everything came to a stop, as long as all that energy turned to heat, that wouldn't violate conservation of energy, right? And so you might argue that, hey, we could do it from a conservation of energy standpoint. But there's more than conservation of energy. There's also conservation of momentum. And conservation of momentum says, no way. You've got a moving cart. And if this cart is moving, it has momentum. And so after the collision, you are still going to have momentum. You're going to have the same amount of momentum. Now the speed may be very small if this has a lot of mass, but you will have some momentum. You will have some movement. And because you have some movement, you have not converted all of the energy into heat. Fair enough? Okay, so hopefully I'm not doing anything surprising here. What I am really saying is the laws of our mechanics is what we've been doing, right? They tell us what can and cannot happen. Well, we have not yet been introduced to the second law of thermodynamics. We have been introduced to the first law of thermodynamics, but I'm trying to point out that for something to happen, the first and the second law allows us and tells us things that could happen, but it also tells us things that could not happen. We need to understand these laws of physics to understand what we can and cannot do, what is possible and what is impossible. That's why we have these big, powerful laws, these very few fundamental principles that explain a universe of phenomena. Okay? That's why we keep working with this. So let me change the game here a little bit. Let me ask you this. Could this happen? Could I take a hot piece of aluminum, let's just say 100 degrees Celsius, like we did in the lab, we take it out of the boiling water, here is 100 degrees Celsius. And then I'll take this piece of brass, which has just been sitting in the room. So we will say it starts at about 20 degrees Celsius. Could I put it together? And could this cool down, let's just say 10 degrees at one moment in time? It may do more than that later on. But could this cool down 10 degrees? Yeah. Could it cool down 10 degrees without this warming up? Why not?
If you're talking about an isolated.
Yeah, now in an insulated, isolated system.
Where else to go?
What has no place to go? Okay, so what you are really doing here is you're saying, look, if here's my block of aluminum, for it to change its temperature, and if this is aluminum, I don't know if you remember from the lab, this was about a 90-gram sample of aluminum. The specific heat was about a 2.15 calories per gram per each degree Celsius. And if I'm asking you for it to cool down 10 degrees, you would say that much energy, 90 times 0.215 times 10, has to come out of it. That is 193.5 calories has to come out. So when I ask, could the aluminum cool down by 10 degrees? Sure, but what's the condition? This same Q has to go somewhere. You are applying the first law of thermodynamics. You are saying, yes, it could cool down with restrictions. You are saying what could and could not happen. You are clearly saying what could not happen is you are saying this could not cool down 10 degrees and this not change its temperature. What you're really saying is the brass must also warm up. All right, so let's do the brass. Q mc delta T. If that same energy, 193.5, went into the brass, and if you remember, the mass of the brass was about 270 grams. The specific heat was about 0.093. And so really what you're saying by the first law of thermodynamics is aluminum could cool as long as brass warms. Brass warms how much? Yeah, 193.5 divided by 270 divided by 0.093. And so if the brass warms up 7.7 degrees, then you would say it's possible, right? And so that's the condition you've placed. You've applied the first law of thermodynamics to it. Okay. What about this? So here's my 100-degree aluminum. Here's my 20-degree brass. The first law was very clear that the aluminum could cool, right? But only when the brass warmed. And the numbers have to be this way. That if the aluminum cooled down first 10 degrees, then the brass would have to warm up 7. Could this happen? Could the brass cool down 7.7 degrees? And the aluminum warm up 10 degrees?
No, because that's like moving from low potential to high. You need energy.
So why can't it happen?
Because you need energy to do that.
Wait, isn't this cooling down losing 193.5 calories of energy? And isn't this gaining 193.5 calories? So I don't understand what the violation is here. The energy is conserved, isn't it? One lost it, the other gained. What's the problem?
You can't move from low to high without energy.
And so do you see this is not a violation of conservation of energy? When I asked you, could you collide into this object and convert all the kinetic energy to heat, in terms of energy, you say, sure, why not? You could just take all the kinetic energy and make heat. But when we added the second condition here, conservation of momentum, the answer was you couldn't do all the conversion of heat. Fair enough? And so what's missing is a teaser to this. There is nothing in the first law that says that is impossible, other than the fact that most of you are looking at it like that. No, that can't happen. But when pressed for a reason, you could not give me a reason based upon conservation of energy. Because the cold one loses 193. The hot one gains 100. There's no violation of conservation of energy here. There is, however, a violation of the second law of thermodynamics. And so you're absolutely right. It can't happen. But that's my teaser into there's a lot going on here in every principle. We've got to obey every law of physics, not just the first law, right? And that's the second law. The same thing could be said here. Could this piece of aluminum be left alone and shoot up and hit the roof? Now, of course, you laugh. No way, right? Why not? Needs energy? I claim that has a lot of energy. Got temperature, right? I mean, quick calculation here. How much energy would it take for that aluminum block to jump up and hit the ceiling? And how high is the ceiling? 3 meters? So if I said the gravitational potential energy, mgy, the mass of that thing, as we've pointed out, was 90 grams. G is 9.8. It's got to go up about 3 meters. The amount of energy for that thing to hit the ceiling is only 0.09 times 9.8 times 3. This is 2.65 joules. If I remember, there is 4.18 joules in 1 calorie of energy. This is only 2.14, or 2.56 divided by 4.18. This is only 0.633 calories of energy. That would correspond sorry, 90 for the mass, 0.09, oh, what am I, aluminum? Yeah. So 0.215 delta T. So if I divide that by 90, divide that by 0.215, that's a change in temperature of only 0.03 of a degree. That's hardly any energy. So doesn't this have plenty of energy? I mean, this thing, according to what you're telling me, doesn't have enough energy. Bullcrap. This thing can shoot up to there and have enough energy as long as it also cools down by 0.03 of a degree. So I ask again, can it shoot up to there without me touching it?
No, it doesn't have,
No, why not?
it doesn't have enough kinetic energy. Yeah, exactly.
Well, can't you convert thermal energy into kinetic?
Yeah.
So why can't it do that? You keep telling me it can't do it, and I'm not hearing a good reason why it can't do it. I know there's a force down, but so what? When I throw a pin up, it still goes up. It has enough energy. Why can't it?
The energy isn't directed in only one direction.
Oh, okay, so let's make it directed in one direction. So what? I mean, that nothing in the first law that says that, right? Didn't the first law say we can convert our energy back and forth? Isn't that the conservation of energy? So,
But it doesn't do it by itself.
okay, so you're getting down the road of you're realizing that those molecules are going in a random direction. If they all went in the same direction, wouldn't it be shooting up? But they're not doing that. And that is the second law of thermodynamics. It is more about a randomness, a random motion. There is nothing here that says from the first law that it can't go up there. Just like from the first law, there is nothing saying this cold one can't get colder and the hot one get hotter. But as we will soon see, this doesn't happen. As you obviously told me, this does not just automatically jump up there. And what I'm trying to say, and that's why I went back to this mechanics, is there's a lot going on. It's not just conservation of energy. In this case, it's conservation of energy and conservation of momentum. In this case, it is the first law of thermodynamics and the second law of the thermodynamics. And we need both of these laws to help us say what can and cannot happen. And so bummer, I probably shouldn't have erased it, but that's what I wanted to emphasize here in the first few minutes of this chapter is for what can and cannot happen. Just like in mechanics, we have Newton's 3 laws of motion and we have the 3 conservational principles. We explained everything that went on in mechanics, what can and cannot happen because of these laws of physics. The same thing in our thermodynamics. We need a first and second, and we had a 0 law, and then we can even talk about the 3rd law, but the 2 big ones here are the first and second law of thermodynamics. And we really haven't introduced you to the second law quite yet. And so that's what this chapter is all about. What is this additional restriction? What does it imply? How do we, of course, use it to say what can and cannot happen? And your author takes kind of a historical approach, so I will too, into the development. He starts off here with what we will call heat engines. What is a heat engine? Well, if I may, you watched me build one once before. It's perhaps not the most exciting engine to watch run, but this is what you saw before. Here is a heat engine. If I were to take that gas and warm it, it lifts. Oh, might as well lift something, right? It's doing work. And so last time I had like a little tray, and so it lifted that one. If I then cool it down, and that's going to be the magical step. Cool it down. Get started again. Could I lift up a second one? This right here, what am I really doing? I am changing heat energy into work energy. That's what's meant by a heat engine. The heat engine is some kind of mechanism, and as we'll see here in the next, we're going to run out of time, but bummer. But for the little time we have left, is we will watch that there are many ways of building a heat engine. But the key to a heat engine is saying, let's put in heat. And however it is done, something takes place where that heat will turn into work. Can all the heat turn into work? And if you say no, I'm going to ask, why not? And fair enough, we have not yet answered it. It looks like we're going to run out of time to completely answer it. But again, can this block just shoot up and hit the ceiling? No. And it's not because of the first law, right? It's because of what we have yet to talk about, the second law. The same thing here. As scientists started building this, they thought, how great, you can turn all of your heat into work. And so every time we heat something up, we can just convert it. And the world would be great if that was our only restriction. But it's not. There is something else going on when you are adding heat. There is what we are going to refer to as entropy. We'll give it a symbol S here for a moment. Entropy is something buried inside of heat. Which, by the way, is the whole reason we never even mentioned the word entropy when we did mechanics. We never had this new law, the second law of thermodynamics, and the conditions that go with the second law of thermodynamics. Because entropy is only associated with heat. That's why when you are putting heat in, you are also putting entropy in, which I know we have not really talked about what it is yet. But let me just say, flowing into that machine is entropy. So when I go to reset the machine, if you will, and get it back to its starting point, I have to take this energy out, but I also have to take out the entropy. The entropy can't come out here. So for me, I've got to do something else for the entropy to come out. The entropy is buried in heat energy, and so I, in this case, put it in something cold. And so I easily put the energy in by putting it in something hot. I wish, to be quite honest, there was no such thing as this entropy. Then I could take the heat energy out all by work, but unfortunately, I'm restricted by the second law of thermodynamics because I got to get that entropy out, and the only way I can get it out is when I take some heat out. And that means if I'm taking heat out, what does that say about the work? It's got to be less than the heat I put in. See how those two laws are beginning to play together? Just like the two laws here about conservation of energy and conservation of momentum. It might be nice to convert all the kinetic energy to heat. And if all I look at is conservation of energy, it looks like I can do that. But because I have the other restriction with conservation of momentum, there has to be a little bit of movement after the collision. If there's movement after the collision, there's kinetic energy after the collision, which means I can't convert all the kinetic energy into heat. And that's the same challenge we have here in our heat engines. We have this new thing called entropy. And we've got to take the entropy out, and we can only do that through heat. And so when we do that, we see that the work will always be less than the heat that you put in. You can never, unfortunately, get as much heat energy, as much work out as heat that you put in. Somewhere there has to be the heat coming out. That's why I put it in this cold place. That's why your car, which burns gasoline, what pushes your car? Those hot molecules, right? Your car is a heat engine. You take the gasoline, you burn it, you make that heat and hopefully convert it to kinetic energy. But can you convert all that heat energy into kinetic? No. It would be great if we could, right? We can't. And so what ends up happening, because the second law of thermodynamics is saying we've got to take some of the heat out by heat. We can't convert all the heat into work. The first law says we could, but the entropy gets in our way and doesn't allow that.
So less entropy is better than per gallon? Or it's not
I'll say yes to that for the moment. The first one, yeah, that I am probably getting better efficiency as less entropy.
Do you have control over how much entropy goes in?
Depends how you design the engine.
So you could control it?
Oh, sure. And that's the whole idea. We can make engines that are actually pretty efficient. And usually to do that, we make them run kind of slow, and they're not very powerful. So we can make little tiny cars with 45 miles to the gallon, 50 miles to the gallon. Or we can swap that out for a big powerful car and get 20 miles to the gallon. And so there's kind of that trade-off in there. But this is going to be our diagram. This is how we are going to represent heat engines. Let's, like I said, look at a few of these so that hopefully you'll have an understanding. This is my simple engine. Here it is. If you want to think of this as burning the gasoline, here's the heat going in. It does some work. But for me to reset it, I got to take and start again, taking the heat out. And so as I do work, I am putting a lot of energy in. Some of that is doing work. What's left over is taken out here to reset it. And fortunately then, not only did heat go in here, but the entropy that went in here came out here. And so I can run this thing as long as I am restricted to both the first and the second law of thermodynamics. It's why I started to turn on this overhead. Did it go on? And say, let's look at the basic operation well, that's weird.
It was on.
It was on.
Let's look at the basic operation of what is going on inside your car. Where's, well, give me a browser, Chrome will work. Where's our web page? Where's our physics? Here we go. Okay, so if I come down to, let's look at how does a typical automobile engine work? This is again what we would call a heat engine. The design here is to put heat in. The whole reason you put gasoline in your engine is so you can burn it. And it works simply like this. If you're not that familiar, we call this a 4-stroke engine because each time the piston goes up and down is referred to as a stroke. This would be, I'll call the fourth one, the exhaust stroke. Here's the beginning. Notice air and fuel comes in. Valve closes, compresses, spark ignites, burns. That's the power stroke. Valve opens, and then we have the exhaust. And so there are 4 strokes here. The first one, as it comes down, let's get back, there's the exhaust. Notice this valve is going to open, the intake valve. It's going to fill up with gasoline and oxygen and nitrogen. The idea then is once it fills up, both valves will close and this piston will come up and compress. That's why it's called the compression stroke. Once you get up a tight little space, the spark plug makes a little spark. You can imagine what's going to happen now when you have spark, gasoline, and oxygen all mixed in there. It's going to burn. That burning makes the temperature go really high. That makes the molecules move around. That pushes the piston down. That's the power stroke. That's the main part of the engine. Here it is, power stroke, pushing it down. Now, the exhaust valve opens up, so when this comes up, it pushes it out, and that's what comes out your tailpipe. And so what comes out your tailpipe is some exhaust gases. They have, of course, cooled down because when it burns, it expands out. But if you've ever got your hand near a tailpipe, you probably would not call it cold. It is a lot colder than it was when it burnt the gasoline, but it is still what I would call very hot. That's this part. That tailpipe is important because not only is heat coming out, but entropy. And our engine would not work unless we let some of the entropy out. And that's our second law of thermodynamics. And so this is the basic operations of what we'd call a 4-stroke engine. Again, I don't know if this kind of looks the same, but I'd put it here. This is burning the gasoline. Power stroke. This then is getting rid of it, cooling it down, and the exhaust. The other stuff is more getting the gas in and burn it again. And so it doesn't quite match that process, but that is the 4-stroke engine. Let's look at other designs. How about what we call a 2-stroke engine? It has its advantages and disadvantages. One of the huge advantages is it only has 2 strokes. Its operation is very simple. You get power every single time. And so this piston going up and down brings in fresh fuel and oxygen right here. It actually uses the motion as the pump. Here is the carburetor and fuel coming in here. As this goes up, it draws it in. As it comes down, it squeezes it and pushes it into the piston here. So the way the new gasoline and oxygen gets in there is this is acting not only as the mechanism of pushing the engine, but it's also acting as the mechanism of pumping the gas in. You don't have a fuel pump here. Notice it's crowned a little bit, so of course what happens is when it comes down like this and it pushes, it hopefully ricochets the fuel up here and not just out this. This will be the exhaust. And so when it gets in here and it compresses it, the spark ignites, pushes it down. As it opens here, hopefully the high pressure will chase most of the exhaust gases out of it. And so again, very few moving parts. It tends to be lightweight. These are great for chainsaws. I mean, you make it out of a chainsaw, you're going to get a lot of power in a little space. You don't have other moving parts, including parts that oil it. So any of you who've worked with 2-stroke engines, what's the thing you have to do? Yeah, you need to mix oil with your gasoline, because as this gasoline flows through the engine, you are trying to lubricate the different parts there, and so you're letting that motion do the lubrication. Yeah?
Is there a 2-stroke diesel?
I don't think so, but don't hold me on that. Oh, in fact, was it this class or the last class? I think it was the second class. Somebody asked me that, what was the coldest time of the day? Was that was you? Yeah, and so I learned something this weekend. It is after sunrise. It's not right before sunrise. It's a hair after.
That's what I said.
Well, it is what you said, and you were asking why. And I was like, hey, I never heard that before. But yeah, no, it is, because and basically the answer is the sun starts to warm, but at sunrise, the angle is so low that it's not raising the temperature as fast as the Earth is still cooling by radiation. So it's about 30 minutes after the sunrise before you turn enough into the sun to get enough solar radiation to start warming it up. So
I heard something about how the vaporization of the dew and how it absorbs energy and it releases,
and that too, but even without other effects like in that case latent heat, but also cold fronts moving in and out, the radiation is still about a half hour more. And that I didn't realize. The vaporization of the water, that made sense, and I always kind of understood that one, which is kind of why Santa Barbara in summertime doesn't warm up until after 12, because we've got that marine layer that is constantly evaporating and evaporating and evaporating, and finally the marine layer burns off, and so about noon then it finally gets warm. Yeah.
So if you're taking out heat as much as you're putting in heat, would the work be done by putting in heat equal the work being done by taking out the heat?
Well, I'm glad you asked. I was going to show you some more mechanism, but let's apply some math here. So what you are saying then, or what I'm trying to say, and hopefully what you're trying to say, is this number, work, can never be equal to the heat you put in, because of this added factor that I really haven't had a chance yet to explain, called entropy. But what it does mean from the first law is that if I take the work and the heat that comes out, that has to equal the heat that goes in. And of course, I also mean absolute values here, since we can get in a debate about pluses and minuses and going in or out. But using just absolute values, this would be my first equation from the first law.
Work. Is that like the work done by putting the heat in plus the work done by taking the heat out?
Well, that's the work done by the motor.
Which is the total.
Right. So if we're looking at an engine here, if this engine is a chainsaw, then the work is actually the movement of that chain and the cutting of the wood as the chain goes around. So that's the work being done by the chainsaw.
Well, like looking at it, half of the circle is done by heat and the other half is done by cooling it down, so to speak. The piston doesn't go back up until it starts cooling down.
Yes. So I'm going to have a process that, whether they happen at the same time or not, I think you're saying these are different. It's doing work, and then the other half of the cycle, it's cooling. Okay, fair enough. And so those are actually two different parts of the cycle. And so there are many different engines, but the point being is no matter what engine we talk about, if they're heat engines, this would have to be true. That process has to take place. Which, as long as you're asking about the math then, let's talk about the efficiency of this engine. We will call this the thermal efficiency. We'll give it the symbol E. But what we really mean by this is how much work do you get out of this engine compared to how much heat you put in. That's your efficiency. Notice again that because of the second law of thermodynamics, we cannot get this to be 100%. It is impossible to say that we will get 100% here. We just cannot get 100% because of the second law of thermodynamics. The first law of thermodynamics would say we could, but the second law is saying no, we've got this entropy issue we've got to deal with. And so if I write these two together, then the work would be that. The work is subtracting the two, and maybe I should keep emphasizing that I am just dealing with absolute values here, because sticking to our tradition from last chapter of pluses and minuses, this wouldn't really work here. But when I simplify this, the efficiency then becomes 1 minus the energy that comes out on the cold side compared to the hot side. So obviously the goal here in the engine is to convert as much as the energy as possible coming in into work, which means we want our efficiency as high as we can And that means, of course, one of two things. We either have the energy coming out as minimal as possible, but of course we're going to have, well, we'll see, that entropy issue, so we can only make it so minimal. Or the other option is to make it a very high temperature. And so the higher we can make our hot temperature, the better off we can be. Let me show you other engines. You might actually like this engine, or maybe a little less popular or common, is the Stirling engine. And so low on time, let me get to the grand finale here. But what if you have one side that is hot and one side that is cold, which is what this little engine is for? I will take my plate and put some ice in the bottom. And down here, I will place this simple engine, a Stirling engine, so that that bottom plate is cold. Now I'll give it a second or two to cool down, and let's talk about this engine. This engine actually has what we would call a displacer. That is this big styrofoam piece under here. That big styrofoam piece cold enough yet? Oh yeah. That big styrofoam piece, as the name implies, is a displacer. I mean, let's think about it. What is happening here? When this displacer is, say, up against the hot one, that means the molecules are near the cold one. They're cooling down. On the other hand, when the displacer is near the cold one, then the molecules are near the hot one. At that moment, when they're near the hot one, which I just passed it, but right now, they're warming up and they would push that down, which would make the wheel turn, which then is connected to the displacer, which pulls the displacer down or back up to here. When that happens, the molecules move over here, cool down, make a vacuum, and that goes back in because the molecules on the outside are hitting harder than the ones on the inside that are cold. And so by changing the location of the displacer, we are making the molecules in here go hot, cold, hot, cold, hot, cold, which either pushes the piston out or cools them down so the outside molecules can push the piston back in. And so we get, again, a heat engine. We get work being done by putting heat into it. In this case, it's the heat of the room. And so this top plate is at room temperature, and this cold plate, of course, is at the temperature of the ice. We could switch that. That's what this other little Stirling engine is, but I probably am out of time, but I'll start it nonetheless. If I fill this crazy thing with alcohol, I could make the hot side cooling fins, cold side, displacer, and piston. And so, maybe. Burn the alcohol, and this takes a couple minutes to get started, so I think we're going to run out of time. But this is a nice Stirling engine also, and it too is going to have a hot side and a cold side. And that is the idea of a heat engine. And maybe that will be a good place to stop. What about the reverse of this? A refrigerator or heat pump, exactly. And I guess that's where we'll start. Tomorrow is, what if I took energy from the cold one? So energy that's in the refrigerator, take it out, keeps the refrigerator cold. But I'm going to have to put work in, and I got to watch my entropy.
Man, I need to get that rectangle done. So why don't we do it like an hour? Because I want to work.
But
can you play the rotary?
We'll have a little more.
Flash?
Oh, is the rotary flash on there?
I thought I said cycloid. Oh, never mind.
I know we had one at one point. But I'm trying to think of where I thought.
So where is the power band in a two-stroke engine? You know what I'm talking about?
Where's the power?
Versus the power, no, the power band. There's like that range where it's like a...
It's essentially just like a four-stroke in that case. So if you go...
What if you spun this the other way?
No. Yeah, it should be slowing it
Can go
down.
one way. How come we can't go that way?
Well, because the timing between the spacing of when this piston has to be down when you're heating it up, so that it'll push it up. If you try to push it the other way, then what happens? Yeah. If I made the bottom hot, it would actually rotate the other way then, because I'm doing exactly the opposite rotation, and I want the molecules to do exactly the opposite. And I really like this one because it's
cute.
The thing about internal combustion engines is everything's internal. You don't really see what's going on. But they call these external combustion engines. You can see the heat and you can
Going pretty fast.
then get it moving. Yeah, and it would go really fast. We used to have a wick. It works better when there's a wick, and it makes kind of like a shooting flame on it. But it got all gummed up, and so we just took it off and just made it a pool of alcohol. It still works, but not to the same level.
What time you think?
Saturday, it's probably 6:30 or something.
Oh, okay, yeah, I can probably that's great.
Yeah, and then I'm assuming trying to study a lot.
Okay, I'll go for an hour. You want to go for an hour?
So I'm trying to be doing like a bit every single day. So
Yeah, that's the right way to do it.